So linear systems, discrete time dynamical systems, are boring. They either go to 0 or they go to infinity. Now I want to talk about an interesting example. And in this example, I'm drawing on, and everybody's drawing on, a very important paper by Robert Mae, later Sir Robert Mae, later Lord Mae, was Her Majesty's scientific advisor and a very famous professor at Oxford for many years. He had a groundbreaking paper in Nature in 1970. And the title of the paper is very, very interesting. The paper is called Simple Mathematical Models with Very Complicated Dynamics. Now, that's a heck of a title, and I want to stare at that for a second, because it's absolutely correct, and it could be not a bad description of the whole phenomenon of chaos. That simple mathematical models can give you a very complicated output. We just saw an example of that, the 3-variable food chain differential equation. Pretty straightforward, gave very intricate and complicated dynamics. We have a default assumption, I think all of us do, which is wrong, which is that when you see a complicated output, there must have been a complicated input. If you see a lot of variability in the output, there must have been a lot of variability in the input. And that's just not true. And we've seen one example, and Mae is going to present an even simpler example, which has now become a kind of an icon of research in chaos. So Mae was indeed interested in a discrete time dynamical system, xn plus 1 equals f of xn. He is an ecologist and was particularly interested in the case where x is the size of the xn, I should say, is the size of the nth generation of some animal species. So he's thinking about situations which are described as non-overlapping dynamics, where the first generation, let's say annual locusts, the number of locusts in the summer of this year, the number of locusts in the summer of next year, the number of locusts, these are non-overlapping generations, and so we can indeed write x1, x2, x3 this year, next year, or this month, next month, depending upon the lifetime of the animal. So xn is the size of the animal population, big, small, whatever. And he wants to find an f. And so then obviously if xn plus 1, we have a birth rate, and that birth rate is b times xn, and that's the only factor there is, then we're back in the linear discrete time system. And if that birth rate is greater than 1, then the population is going to explode to infinity. And if that b is less than 1, the population is going to die to 0. And he's interested in a more complicated situation. He wants to know, and this model is going to reflect, what happens when you can't grow to infinity? As, of course, you can't. Why can't you grow to infinity? You can't grow to infinity because you eventually run into competition for finite resources. Among other things, the Earth is a finite surface. And so this can't grow to infinity because pretty soon, no matter what the animal is, they're going to start crowding each other. So you may remember this whole crowding argument, and you may remember the logistic differential equation. And the logistic differential equation said x prime is a birth rate times x times a crowding factor. And the crowding term has the form 1 minus x over k, where k is the carrying capacity. And what this is saying, just to remind you, is that if x, the current population, is less than the carrying capacity, then this fraction is less than 1. 1 minus this fraction is positive. This term is always positive, and so the population grows whenever x is less than k. If x is bigger than k, this fraction is greater than 1. This whole term becomes less than 0, and x prime becomes negative. And so in the differential equation, this is the smooth approach to the stable equilibrium at x equals k. Now, let's throw in a complicating wrinkle. And the complicating wrinkle is we have discrete time generations, not continuous time. So we ask, what does xn plus 1 equal bxn times 1 minus xn over k? What does this dynamical system look like? Now, he's going to make a technical assumption here, which is generally made, and we're going to follow it. Instead of looking at numbers like 3,722, we're going to let k equal 1. And by letting k equal 1, we're turning x into some fraction of the total. So now x is going to vary between 0 and 1. X is going to be drawn from this interval 0, 1. And now we have to ask, well, what kind of dynamics is this system going to produce? The simplified form is called the Mae equation. It's xn plus 1 equals r, which is our relativized birth rate, xn times 1 minus xn. So this is obviously a nonlinear system, right? There's a minus x squared in there. So the behavior is not trivial. We don't know what this looks like. But we can just experiment, and we don't even need Euler's method. We just need to have this function f built into our program, and then we just need to keep pressing the F button again and again and again and generating our long-term dynamics. So I'm going to pick a value, and you'll see why I'm picking this value in a minute. I'm going to pick the value r equals 4, but I want to stress that what I'm about to show you does not depend upon just having this exact value, 3.9, 3.95. Anything in a certain interval is going to give you the result that I'm about to show you. But let's let r equals 4, and let's just pick an initial condition, x0 equals 0.2. And let's ask ourselves what happens if we start with x0 equals 0.2 and just keep pressing that F button again and again. The answer is very interesting because the output looks like this. Now let's stare at that for a second. Notice something. Number one, it's irregular. Is it periodic? No. Here's big excursions, here's little excursions, here's halfway excursions, here's big ones followed by little ones. This output is not periodic. And in particular, as we saw, that means that it can never repeat. Each of those white dots, remember the data is the white dots. The data is not the lines connecting them. We're just drawing the lines connecting them to age or I and seeing the progress. But if you look at the white dots, they are absolutely not repeating each other. And once again, we have to make the qualifier that they are not repeating each other in the pure math where we have infinitely long real numbers and a particular data point is a mathematical point in that interval 0, 1. In a computer, we don't have infinitely many possible values of x. And therefore, if you could press that F button 100 million times, sooner or later you would have to repeat the same value in the computer, but not in the mathematical function. It is easy, not easy, it's possible to prove that this function never repeats. And if you took all of those dots and you projected them onto the x-axis, you would get a scattering of points that never repeated itself and that kept filling in between previously existing points. It would put in another point. So, property number 1 of the Mae equation with r equals 4 is it is aperiodic. Number 2, it is bounded. It's very easy to show that as long as r is less than or equal to 4, if you pick an x that is less than or equal to 1 and goes between 0 and 1, that f of x also is between 0 and 1, and f of x is also between 0 and 1. So this function will jump around, but it's always going to stay in that interval. So it's bounded.